I'm Anders Musikka, as we just heard, and I'm an engineer at Helsing. And we're hiring, so come by our booth. It's like right over there. So let's say you're writing a computer game, and you have several assets, like graphics or whatever, and you want to share them between different threads. So you might use like arct, like atomically reference-counted pointer, the standard type in the Rust library. And then you realize you want hot reloading, right? You don't want to have to restart the game every time you change the graphics or something. So you need, like maybe you want to use ArcMutex, but then multiple threads cannot read the same asset at the same time, and that won't be good. So you want to use RwLock. And here's some example of like AAA quality 0.2 kilopixel video game art, right? And we'll use these as examples in this talk. So here's the disassembly of an arc deref on the left side, which is just reading a pointer value from memory, incrementing it by 16, and there you have it. So it's super fast. And on the right side, we have RwLock, read access. And I mean, this is not as bad as it seems, because most of this is not on the hot path, right? But crucially, there's an atomic write in the RwLock case. So to read memory using an RwLock, you actually need to write to memory, because each reader must increment a reference counter so that subsequent writers know that they have to wait until the reader is done. And this turns out to be quite costly from a performance perspective, as we will see later in this talk. So let's look at the data layout of an arc. It's just a heap block with two counters and your inner value, an apple in this case. And now we want to change the apple to a banana from A to B, right? And what if we could add a next pointer to the heap block of the apple? And then we could, when we want to update the value to banana, we just point the next pointer at the banana. And the next time the user of the arc, the next time the arc is dereferenced, it can notice that the next pointer is no longer null, can follow the next pointer, and it's pointing to banana, and then presumably we do some reference counting magic to be able to deallocate the apple. Now consider this case. We have two arc instances sharing the apple. Arc2 updates the apple to banana, and then for some reason we hot reload again and it updates to cranberry. But the first instance hasn't yet been accessed, so it's still pointing at apple. Now in this case, we could deallocate banana. We couldn't deallocate apple or cranberry because those instances could be read from at any time without having to do any kind of locking. But if we deallocate banana, what's to say that arc1 here hasn't just read the next pointer, and it's just about to access like increment the weak counter of banana? Well, nothing. And if we then deallocate banana, we could have undefined behavior. So that's no good. So how does ArcShift work? We take the arc, like architecture, and we add next, previous, and advanced fields. Next points to some node with a newer value, with a later value in the sequence. Prev is always exactly the previous node. And advanced is used to protect the next value in the chain of values, because we had this chain here, right? Protects the next one from being deleted. We have two main algorithms, advance and garbage collect. And this is a lightning talk. We won't have time to go into the details of garbage collect. And frankly, we won't have time to go slowly through advance either. So I'll just go through this very quickly so you can get a feel for approximately what happens. So arc1 wants to advance. It's pointing at apple. It notices that the next pointer is not null, so it needs to move to the right. So what it does, increments the advance counter, which protects banana from being deleted. Now it's safe to dereference the next pointer, increment the banana weak count. Now that we hold a weak count on this, no one is allowed to free it. So we can decrement the advance count. We do this again for banana. And then we increment the strong count for cranberry, the latest value. And at this point, we can decrement the strong and weak counts for apple. And the details of this, just come talk to me afterwards if you're interested. We won't have time to go through it. And at this point, we can run the GC algorithm, and then we can deallocate both apple and banana in this case. But we won't have time to look into that right now. So, benchmarks. I've heard it said that all benchmarks are lies, and I think there's a lot of truth to that. Especially these benchmarks that are micro benchmarks. But I think this still has some information. We can see that the RwLock read micro benchmark is about 10 times slower than the ArcShift read. And that does make sense, because the ArcShift read is just a relaxed atomic read and a comparison. And the RwLock has to write. And if we look at this under contention, so what I've done here is I have another thread that's constantly just reading the ArcShift or reading the RwLock. We can see that the RwLock now is 100 times slower. And that's because in the RwLock read case, the two cores are just ping-ponging a cache line back and forth between each other. But for ArcShift, the cache line will be in the L1 read cache on both cores, and they no longer interfere with each other. Update is slower because ArcShift is a more complex algorithm, more complex data structure. And it's about, as you can see, like, I don't know, 5 times slower or so. And here are the same benchmark numbers in bar graph form. And you can really see how under contention, RwLock is, well, it's 35 nanoseconds. So I wouldn't say slow, but slower than other mechanisms. And for writes, yeah, ArcShift writes are more expensive. So ArcShift is a lock-free algorithm. And I think Ali this morning showed us an example of a non-lock-free algorithm with the try lock in a loop mechanism. And that wouldn't have been lock-free. Because when a lock-free algorithm has to retry something, that has to be because some other thread made some kind of progress. And crucially, if a thread is just stopped, like not scheduled for a while in a lock-free system, that can't cause other threads to have to wait, because then it's not lock-free. We have wait-free algorithms also, and that's much stronger guarantee. A wait-free algorithm always finishes in a bounded number of steps. So, I think some of you might be thinking right now, this seems really scary. This is like a lock-free algorithm in a crate, which is like not very well known. And yeah, getting this correct is quite hard. Especially like being able to test all the various code paths that might be like executed is very hard. It's hard to find these paths in the tests. And the number of possible schedulings in an algorithm like ArcShift becomes huge. So what we do is we use testing tools such as Loom, which I can really recommend. So it's a kind of testing harness that will explore exhaustively, if you want, all possible schedulings for the various threads in your algorithm. And of course, the number grows very quickly. So if you have a complex algorithm and many threads, it becomes infeasible. We have Shuttle, which is a bit like Loom, but it's not as precise, especially when it comes to memory ordering. But it's much faster. And we have Miri, which many of you probably know, which also can detect threading bugs. You can actually run Miri with this many seeds flag to get it to try many different schedulings of your multi-threaded program. And we also use cargo mutants that Andre talked about this morning. And that's like really frustrating, but really cool. It changes your code and makes sure that your tests actually fail when the code is changed. And we do this kind of exhaustive test where we take the primary operations of ArcShift and we run all possible combinations of them on like 3 threads. And this can get quite slow if you run it on the Loom. And the other techniques, we check that after each test, we check that all the pointers are still consistent with the reference count. So if a reference count is 3, there should be 3 pointers to that node. We have a special dummy payload that just detects memory leaks. So we allocate an instance of this, we put it in the ArcShift, and then we make sure that the object has actually been dropped. And just dropped once, right? We test with the panicking drop implementation. So ArcShift is wrapping a user-supplied type, right? And that has a drop implementation, perhaps, and that could panic, potentially, and then we shouldn't have undefined behavior. So we need to test that. We test payload types that are too large to fit on the stack, which is can be a challenge. We have recursive structures, and we have sending ArcShift instances, because ArcShift instances are send if the type they wrap is send and sync. So, in conclusion, you can use ArcShift instead of RwLock, and depending on your workload, it might be faster. It's fast for read-heavy loads. It's not going to perform well if you have write-heavy loads, or if you rely on being able to modify the inner value in place, because you can't do that with ArcShift. You have to supply a new value. It's lock-free, which can be good if you're scared of deadlocks. Has no dependencies, and it supports no STD. And it's available on craze.io as ArcShift. Yeah, that's my talk. So any questions?